Finding the interval of convergence of a power series. A power series centered at x equals a is an infinite series of the form the sum of n equals 0 to infinity of c sub n times the quantity x minus a to the n, or in expanded form, c sub 0 plus c sub 1 times x minus a plus c sub 2 times x minus a all squared plus the general term c sub n times x minus a to the n, and so on. The index can start at any positive integer. So, informally, a power series is an infinite series, but it's also a function of x. Finding the interval of convergence for a power series. We can think about it in two cases. If c sub n is a constant, so this part in front of x minus a to the n is just a number, we have a geometric power series and can find the complete interval of convergence. But if c sub n is a function of n, apply the ratio or root test to find the incomplete interval of convergence. To find the complete interval of convergence, we must test the endpoints. Let's find the interval of convergence of the sum of n equals 1 to infinity of the quantity 5x minus 4 to the n over n. This is not a geometric power series because I can rewrite it as the sum of n equals 1 to infinity of 1 over n times 5x minus 4 to the n. So this is not a constant, this is a function of n. So what we're going to do is apply the ratio test here to find an incomplete interval of convergence. And so remember, the ratio test says that if the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n is less than 1, then we know we have a convergent series. If that limit of the ratio equals 1, it's inconclusive. And that's why we're going to have an incomplete interval of convergence at the endpoints, because the endpoints is where the limit of that ratio is equal to 1. So what we want to do is we want to start by solving the limit as n approaches infinity of the absolute value of this ratio here. So we're going to substitute an n plus 1 into each n. So we'll have 5x minus 4 to the n plus 1 over n plus 1. And then divided by a sub n. So this right here is a sub n, but instead of dividing by that, let's just multiply by the reciprocal, which is n over the quantity 5x minus 4 to the n. So we want to know, when is this less than 1? Because we'll know that's when this power series converges, whatever x values make this limit less than 1. So here what we're going to do is say the limit as n approaches infinity of, I'm going to put n over n plus 1. So I'm going to do a little rearranging here. And then 5x minus 4 to the n, and then 5x minus 4 to the 1, so that we can see 5x minus 4 to the n, those cancel. So now what we're doing is we're evaluating the limit as n approaches infinity of n over n plus 1, because 5x minus 4 to the first doesn't have any n's in it. So here we can use the laws of dominance. These are both n to the first power, so the coefficients are just 1 over 1, so 1. So we end up with just this part being 1, and all that's left in absolute value is 5x minus 4 is less than 1. So if we want to go to the interval of convergence, or the incomplete interval of convergence, we're going to make this a 3-part inequality. So -1 is less than 5x minus 4 is less than 1. And from here, we'll go ahead and add the 4 to all 3 parts. So we'll get 3 is less than 5x is less than 5. We'll divide all 3 parts by 5, so we'll get 3/5 is less than x is less than 1. So this is an incomplete interval of convergence, because at these endpoints, we would get the ratio test equals 1, and that's inconclusive. So we are questioning what's happening at each of these inequalities. So we're going to have to check the endpoints in the original series. So we're going to check what happens when x is equal to 3/5. And we're going to plug it back into the x in the original series. So we're going to have n equals 1 to infinity. We had 5x, so x is 3/5. 5 times 3/5 minus 4, so 5x minus 4 to the n all over n. Well, 5 over 5, whoops, cancels. I guess I could erase it, but cancels. And then we have 3 minus 4, which is negative 1. So what I have is negative 1 to the n over n. And this is the alternating harmonic series. And the alternating harmonic series converges. So we should know the harmonic series diverges, and this one's popular enough to recognize the alternating harmonic series converges, which means that x equals 3/5 is included in the interval of convergence. So we can come back up here and we can now say that this is less than or equal to, because 3/5 is included. And then we have to go ahead and do the same thing and check x equals 1. So if we check x equals 1 in the original power series, we're going to have the sum of n equals 1 to infinity, and we're going to have 5 times 1 minus 4 to the n over n. And 5 minus 4 is 1. 1 to the n is 1. So we end up with just the harmonic series, n equals 1 to infinity of 1 over n. And as we said earlier, the harmonic series diverges, so that means that x equals 1, that is truly not included in the interval of convergence. So we have our complete interval of convergence here. 3/5 is less than or equal to x is less than 1. Now, we were not asked for the radius of convergence. If we wanted to find the radius of convergence, I would suggest going back to this step here. Absolute value of 5x minus 4 is less than 1, and factoring out the 5. So if we were trying to find the radius of convergence, I would take the 5 out of there. I'd get x minus 4/5 in absolute value bars is less than 1. And then I would divide by the 5. So we get x minus 4/5 is less than 1/5. So the radius of convergence is then 1/5, and we even get the center of 4/5, which we can verify here with our interval of convergence that the center, the halfway point here, is 4/5, and then the distance to those endpoints is 1/5 away. Now let's find the interval of convergence of the sum of n equals 0 to infinity of the quantity 2x plus 1 over 3 to the n. This is a geometric power series. We can see that we have just a constant, a 1 in front, and then r to the n, where r is a function of x. So we can go ahead and find the complete interval of convergence without checking the endpoints. And that's because of what we know about geometric series. We know that if the absolute value of r is less than 1, that our geometric series converges. But if the absolute value of r is greater than or equal to 1, then the geometric series diverges. So there's no inconclusive part to a geometric series. So all we need to do is find our r and solve when is the absolute value of r less than 1. So we're going to solve when is the absolute value of 2x plus 1 over 3 less than 1. Let's go ahead and factor the 1/3 out of the absolute value. 1/3 absolute value of 2x plus 1 is less than 1. We'll multiply both sides by 3. So absolute value of 2x plus 1 is less than 3. And then we'll solve the 3-part inequality. So we'll have negative 3 is less than 2x plus 1 is less than 3. We'll subtract the 1 from all 3 parts. So we'll have negative 4 is less than 2x is less than 2. And then we'll divide everything by 2. So we'll have negative 2 is less than x is less than 1. And we don't need to check the endpoints. We know what happens when the absolute value of r is greater than or equal to 1, the geometric series diverges. So they are not included. We're going to keep them as just less than. And so this is the complete interval of convergence. And we can leave it in this inequality notation, or if we want to turn it into interval notation, then we could write x values in open -2 to 1 open parentheses. Now let's find the interval of convergence of the sum of n equals 0 to infinity of -1 to the n, x to the 2n plus 1, all over the quantity 2n plus 1 factorial. This one's definitely not geometric, so we're going to move forward with the ratio test. We're going to attempt to solve the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So let's go ahead and replace each n with n plus 1, so negative 1 to the n plus 1, x to the 2 n plus 1 over 2 times the quantity n plus 1 factorial. And then instead of dividing by a sub n, we'll multiply by the reciprocal. We'll put 2n plus 1 factorial on the top, and then negative 1 to the n, x to the 2n plus 1 on the bottom. So we want to know, when is this less than 1? What I'm going to do right away is just ignore the alternating factors because we're in absolute value bars. And then I'm going to sort of start to group things together a little nicely. So I'm going to focus on the factorial parts. So what I'm going to have is the limit as n approaches infinity. In the numerator, I'm going to have 2n plus 1 factorial. In the denominator, I'm going to distribute the 2 into n plus 1. So I have 2n plus 2 plus an extra 1 would be 2n plus 3 factorial. And then times x to the 2n plus 1 in parentheses plus 1 is x to the 2n plus 3. So we're going to have x to the 2n plus 3 in the numerator, and then x to the 2n plus 1 in the denominator. And I'm showing a lot of work here. If you can already see what's going to happen, you can kind of skip ahead. But here, what I'm going to do is show what's happening to the factorials. So on the bottom, I have the bigger factorial, 2n plus 3 factorial. So I'm going to write 2n plus 3. Then the next piece of the factorial would be 2n plus 2 that gets taken out. And then I'd have 2n plus 1 factorial left over. So that's finally going to cancel with the 2n plus 1 factorial on the top. And then x to the 2n plus 3, that's x to the 2n times x to the 3. And on the bottom, I have x to the 2n times x to the 1. So the x to the 2n's are going to cancel. And now I'm going to write the limit as n approaches infinity. I have 1 over 2n plus 3 times 2n plus 2. And then I have just an x squared left over after I simplify x cubed over x. And then that's all less than 1. As n approaches infinity, 1 over 2n plus 3 times 2n plus 2, that is going to 0. The top is constant and the bottom is getting really big, so that's going to 0. So what I have is 0 times x squared is less than 1. Well, 0 times x squared is just 0. So what values of x make this inequality true? All values of x, right? So 0 is always less than 1. So this is always true for every x value. So that means that the interval of convergence is all real numbers. So negative infinity to infinity, if I want to write this in interval notation.